Hello everyone. In the previous lecture, I discussed about different radiochemical practices. Like, you have good laboratory practices, GLPs for your chemistry laboratory. We have good radiochemical practices, GRPs for a radiochemical laboratory. I also discussed some of the radiochemical separation techniques. In this present lecture, I will discuss the radioanalytical techniques which employ radioisotopes and tracers to study different chemical processes, and also some of the applications in many areas. So let us first discuss the radio tracer concept. The father of radio tracer concept is George Hevesy. In 1920s, early 1920s, George Hevesy developed this tracer concept, and there is a very nice story about George Hevesy, how he first time used radio tracers. I would like to share with you. George Hevesy was actually staying as a paying guest in a house, and the paying guest, means the house landlady or landlord will give you not only the accommodation but the food also. So one day he realized that their landlady is serving the leftover of the previous day to them for breakfast. And so he wanted to do an experiment to confirm, scientifically prove that they are being served the leftovers. So what he did, he took a tracer. Of that time, there was no artificial radioactivity, so we have lead-210. So lead compounds contain lead-210. And lead-210 was, in fact, he just added that lead-210 in the meals. And next day, when he was served the food, he took that portion to the laboratory. And he counted it for beta activity. And he found that lead-210 was present in those samples. So lead-210 is a 20 years half-life, and it is you can separate it from the uranium series. So then he conclusively proved that this lady is serving the stale food to them. So he actually traced the path of food using 210 lead as a tracer. That is what is the meaning of radio tracer. So the concept is like radioisotopes have the same chemistry as their stable isotopes. So you can use them to trace the path of an element. You have, for example, you have a sulfur, a process where sulfur is being used. You can have radioactive sulfur, sulfur 35, mixed with the reactants, and you can know where the radiosulfur is going. So you can, from outside you can trace the path by radiations. So they can use it in industry, environment, medicine, agriculture. You can use them to trace the path of an element. You can use them in diagnosis of diseases by imaging, because you can make them to go to a particular organ, and then they are emitting radiation from outside the human body. You can take a image of, like X-ray you take. Similarly, you can take the gamma image using gamma ray counters. They are used in vitro for determination of different compounds like hormones in our body. I will discuss that. And you can also do the trace element determinations of metal ions, biological molecules using radio tracer techniques. So some of them I will discuss in this present lecture. Radio tracers have a lot of advantages, and in fact, you will notice that many of them over a period of time, when modern techniques not based on radioactivity are being developed, many of them have become obsolete also. But sometimes you will find that they are indispensable. Some of the experiments you will find you can do only with the radio tracers. So one of the advantage of this is they are very sensitive. Suppose you are doing a counting of radioisotope emitting a particular gamma ray, then it is very sensitive because that gamma ray is unique to that particular isotope. They are very simple. Some of the detectors like GM counters, sodium iodide counters are very low cost. So you can carry out even research using this. So low cost instrumentation is one of the important advantages of radio tracer techniques. Of course, it is said that you should use radioactivity for your any experiment or for research or any problem solving only when there is no alternative. So there should be an advantage in terms of manpower, time, cost, and so on. So you save time, you save money, you save manpower. So then only you should be able to justify the use of radioactive isotopes in a research or in solving any problem. So you have to take care, you take precautions like mass effect means because of the very low concentrations of these isotopes, some of them are carrier free. So there is a chance that they may get absorbed onto the wall of the container, So you have to, like I was telling you, use some carriers to increase the mass so that they are not lost. So the low concentrations have their associated difficulties and challenges. When you produce a radioisotope, it may be produced in a particular oxygen state, you don't know. So you have to verify that what is the oxygen state, and then you make sure all the isotopes, all the atoms are present in that particular oxygen. So you need to adjust the oxygen state by using oxidizing reducing agents. Similarly, you are using some isotopes, stable isotopes, like if you are using a tracer of an element, then you have to make sure that the tracer and the stable isotope have the same oxidation state. Otherwise, we cannot trace the path of the element in the process. So suppose tracer is in iodine, tracer is in the iodide form, and the iodine present is in iodate form. So you cannot trace the path of iodate using iodide. So you make sure both of them are in the same oxidation state. Then many times, the radioisotope may decay to another isotope, which is also radioactive, as we discussed in radioactive decay chain, and that may interfere in your separations. So you make sure that if you have a daughter product, then you should also be cautious about interpreting your data. You must know that the daughter product is also radioactive, and you have to factor that into your final conclusions. Okay, so let me discuss some of the radioanalytical techniques which are commonly used, and many of them you will find have become obsolete because there are now much better techniques available. So one may not be needing it, but it is very interesting to see and how people have developed those techniques, and it is so unique about radioactive based techniques. One of them is radiometric titrations. So you, as a radio tracer, you do the norms, for example, precipitation. So you normally in gravimetric type you can precipitate, you can take the precipitate weight and find out the concentration. So you go on adding the reagent, and you will find at some point of time the equivalent point is reached. So how do you track that? So for example, you want to determine chloride concentration in a solution, like you can have sodium chloride or barium chloride, any chloride salt, and you want to do a titration using a precipitation reaction. So silver chloride is insoluble. So you take silver nitrate as a titer and go on adding silver nitrate. This silver nitrate you tag with 110 silver, and silver chloride will precipitate 110, and you are left with sodium nitrate in the solution. So what you do in the burette, you take labeled silver nitrate, and in the solution you have the chloride ions, chloride salt solution, and now you go on adding dropwise the titrant and then record the activity in the supernatant. So the precipitate will settle at the bottom. From the supernatant you take an aliquot, go on taking the aliquots, and you find the activity. So what is happening, as you add the reagent, radio tracer labeled reagent, silver nitrate solution, initially when silver nitrate concentration is low, all of it will be precipitated, and you will see the background in the counter. When all the chloride is precipitated as AgCl, then at the end point 110 silver activity will begin to rise, and that's because there is an excess of silver activity in the solution. So you can then find out the end point, what is the concentration of silver nitrate that is sufficient to neutralize, to precipitate all the chloride. So beyond this, the silver nitrate is not precipitating, it is going up and up because you are just adding the one solution to another solution. So that is how you can find out the equivalent point, and a very simple experiment based on radio tracer counting can be done to do the determination of chloride concentration. Same thing you can do for thiocyanate, silver ions, tungstate, magnesium, and so on. So you can use the proper reagent. For thiocyanate, you can use silver 110. For silver, chlorine 36. For tungstate, you can use cobalt 60. For magnesium, you can use phosphate ions. So you can use the suitable radiotracer labeled titrating agent and do the radiometric titrations. But you will find that nowadays, no, this is not very common these days, because there are much better techniques. You can use them for these experiments. Solvent extractions are still very useful, very commonly used, and they use for separating the different metal ions or different organic molecules. One of the applications is determination of microgram quantities of metal ions like mercury, lead, cobalt, zinc, nickel by solvent extraction with a reagent called dithiazole. So you can do solvent extraction, and you can use the radiotracers of these elements to see the distribution in aqueous and organic phase. So that is the beauty of radiotracers. You can determine the distribution ratio. So suppose you have used mercury, so you use 203 mercury as a radiotracer. So in the aqueous solution, you have the radiotracer mercury 203. After the solvent extraction, some mercury will go in the organic phase, and you can take aliquots from aqueous and organic 100 microliters or 50 microliters and count the activity of 203 mercury in the two phases, and you can find out the distribution coefficient. Suppose you are having multiple elements in the same solution, you can find out the D value for different metal ions, and you can find out the separation factors. So this is for radiotracers, solvent extraction is very ideal system. You can even there are now complexing reactions. You can study the equilibria. So how as a function of acid concentration, how the distribution equilibrium is shifting, as a function of ligand concentration, how the equilibrium is shifting. All those studies can be done using radiotracers. So much so, even you can determine the stability constant of metal ligand complexes. For example, if the metal ligand is going in the organic phase, so you can do, as a function of ligand concentration, you do solvent extraction, and then find out what is the time, what is the concentration of the ligand at which you will see the metal ligand complex is getting into the extraction phase. And then you can set up the equations for finding out basically what you need, the stability constant K equal to concentration of Ml upon concentration of metal into concentration of ligand. This is the free metal ion, this is a complex metal ion, this is the free ligand. So you can find out this ratio. Metal ion free will be in aqueous phase and complex metal ion will be the organic phase. Once you know this, and the ligand concentration is nothing but free ligand plus metal complex concentration, total ligand is known, you can find out the free ligand, and therefore you can find out the stability constant. So this is how you can use radiotracers for solvent extraction. Similarly, the ionic exchange reagents, ionic exchange separations are using radiotracers very frequently. In fact, I give you some very interesting example of even the discovery of trans americium, I can say. See, americium, see, if you see the actinide element after plutonium can exist in 4, 6, and so on. After plutonium, americium, curium, berkelium, californium, einsteinium, fermium, and other elements. All elements are present in the +3 state, called actinides. Now, in the late 1940s and early 1950s, in the different cyclotron experiments, the trans-plutonium elements were being produced and they were being discovered. So how to discover a new element? It was known in 1944 by Seaborg's actinide concept that beyond americium, all actinides are predominantly present in the +3 states. So they are similar to rare earths. They are lighter homologs. So they set up, it was already known that individual lanthanides can be separated by a cation exchange resin. You can load the solution of cations from a dilute acid into a Dowex 50x4 cation exchange resin, and then elute with alpha hydroxy isobutyric acid, which I explained some time back. One by one, you will see the heavier lanthanides come first and followed by the later lanthanides. Similarly, these actinides also follow the same trend as the lanthanides. And so the different lanthanide actinide ions can be seen in the profile of radio tracers of the different elements. Now you don't have the radio tracers of actinides. You can use radio tracers of lanthanides to see the position of individual actinides. And that is how this element mendelevium Z equal to 101 was discovered by Gregory Chopping, the student of LNTC board, by analogy with their lighter lanthanide homologs, and their position in the ion chromatography system was useful in discovering new elements. So this is how the power of ionic separations. You can calibrate the concentration of alpha hydroxy butyric acid to separate individual actinides and lanthanide elements and see their position uniquely in as a function of the drop number in the elution curve. That is what is the advantage of radio tracers. In fact, we have done experiment. We have the tracers of each lanthanide ion at an element, and you can mix them and do the chemistry, and you can see beautiful profile of individual rare earths. Now I will discuss some of the applications of radioanalytical techniques like isotope dilution analysis. This is a beautiful radioanalytical techniques to determine concentrations of some analytes. And isotope dilution, you don't have to do a quantitative separation. 100% separation is not needed. So you essentially, when you isotope dilution means you dilute the specific activity of a radioisotope. So what you essentially do is you have a standard solution of radio tracer, for which the specific activity is known. The specific activity means activity per unit mass. Now suppose you have a quantity M. So specific activity means per gram. This is the activity. This is the amount of the substance. So total activity will be M into S. M into S is the total activity. Now you want to find out the concentration of an unknown analyte Mx. So what you do? You add this unknown analyte with this the standard solution of the same element, but tagged with a radio tracer, and then you measure the specific activity. So you have now the standard solution and the unknown solution. Total, you have your quantity Mx plus M, which will have a reduced specific activity because you have added some inactive metal ion. So this total activity, specific activity in the amount, is same as the initial activity into concentration. So from this equation, conservation of the total activity, you can find out Mx equal to, you can solve this M into S by Sx minus 1. So M is known, what was the initial amount of standard solution, what is the specific activity of standard solution, what is the specific activity after mixing the two, and you can find out the concentration in the unknown solution. That is what is called the isotope dilution. By diluting the specific activity, by what factor the specific activity got diluted tells you what is the concentration of light. Just to give you an example to illustrate this point more clearly, suppose you have a solution of cobalt in 10 ml solution. You want to know what is the amount of cobalt in this solution. So just give some numbers. You have a standard solution of cobalt 60, 7.5 milligram cobalt. Cobalt 60 may be very small. It may be picogram quantity, but amount of cobalt, total cobalt in that solution is 7.5 gram. You count that entire solution and you get 340 counts per minute. So the specific activity of that will be 340 by 7.5 will be 45.3 CPM per gram. So counts per minute per milligram, not gram, per milligram, because it contains 7.5 milligram of cobalt, not cobalt 60, total cobalt. It is cobalt, total cobalt. Now you add to this solution 10 ml of the unknown solution for which you want to find out the cobalt concentration. Then you have to now do separation. So you separate out cobalt by you can do solvent extraction or you can do electrode deposition. You separate cobalt. And mind you, cobalt 60 and so both the solutions should have the same oxygen state of cobalt. So by separation, you got 10.3 milligram of cobalt. So it is not necessary to have quantitative separation. Whatever is the amount you got, and you take the activity of that, and you got 178 counts per minute. So the specific activity will be 178 upon 10.3 means 17.3 counts per minute per milligram of that separated cobalt fraction. So you can put in this equation the value. So S upon Sx minus 1 into 7.5 will be 12.1 milligram of cobalt in the unknown solution. Total amount of cobalt. So the concentration of cobalt in that will be 12.1 by 10 ml, so will be 1.2 milligram per ml. So this is how, so of course you can say that today you don't have to do radiotracer technique because you can put it in a ICP AES, ICP MS. So there are now modern techniques based on spectrophotometry, optical emission spectrometry and so on. So such techniques, sometimes may not be useful, but I'll give you an example, this one. And you will really appreciate the application of isotope dilution technique. Blood volume in human body. Suppose you want to know what blood is there in a particular human being. It's a simple experiment. You can take 1 ml of a patient's blood, take out 1 ml, add sodium 24 activity, 14 hours half-life, and in that 1 ml solution and find out the specific activity. You can count the gamma ray activity of sodium 24 and suppose you got 20,000 counts per minute in 1 ml of that solution. Now this 1 ml you inject intravenously into the human patient and after 15 minutes take out 1 ml. So what has happened that this 20,000 counts per minute activity is got now distributed in the human entire body. Whatever volume we have, it is equated with that in 15 minutes. And now you take out 1 ml and measure the activity of sodium 24. And let us say you got 4 counts per minute in that 1 ml, which you got later. So now you can again put the total activity, initial activity, 20,000 counts per minute per ml into 1 ml. This is what you added. And finally, the volume of the blood is not known in the human body. So V plus 1 ml we added, V plus 1 ml into 4 CPM per ml. And you can find out the V that is equal to 5,000 ml. So this is a total volume. So you can say you can take 1 ml and do that. So the volume of the blood, you can know total body is very difficult experiment. So this is a very isotope experiment can tell you without much difficulty the volume of blood in a human being. So you have to find out the ingenuity in the experiment. So there are some experiments we will find radiotracers offer a unique advantage. Another such techniques is radioimmunoassay. Radioimmunoassay is a technique developed by Bjorson and Rosalind Yalow in 1950s, and Rosalind Yalow received the Nobel Prize for this in 1977. So this radioimmunoassay is actually used to determine minute quantities of substances of clinical interest in biological systems. So if your body has got certain hormones like T3, T4, these thyroid hormones, or you can have many other, in our body there are thyroid globulins, so many antigens are available, and you want to know their concentration as a part of the diagnosis. So this is based on this again. These isotope dilutions called substoichiometric isotope dilution. Substoichiometric means there are two reagents. One is the antigen and one is the antibody, and one of them is in excess, other one is in very dilute, low concentration, so that they are not stoichiometrically being added. So the concept behind is that suppose you want to determine the concentration of this antigen. It is not silver, it is called antigen like T3, T4, TSH or prostate specific antigen in the body. Different glands are excreting different hormones, and you want to determine their concentrations. So we do not know. We take out a sample from a person and you add to that a labeled antigen. So suppose you have thyroid hormones, they contain iodine. You can take an iodine tracer, 125 iodine, and make sure that they have the same oxidation state of iodine in the both. So you have a small quantity of this antigen. You add the two, and now you react them with an antibody. So the antibodies are specific to a particular antigen, but this antibody is in a very small concentration with respect to antigen. So the radioactive and the inactive antigen will compete with each other to bind this antibody. And so later on, you will find that you will have a mixture of, so you can now label, you can form a complex which you can centrifuge and count. So what you are doing now, you are counting the labeled antigen with antibody and find out the concentration of antigen that is labeled. So what you do, this bound activity, this concentration. So you can find the in that total. Actually, this is total, no. So in the total, what fraction of antibody is bound? That is called the bound activity. And as a function of increasing concentration of antigen, so you have to do multiple experiment. So you do, this is like a calibration graph. You take different concentrations of the antigen and generate this graph. As you increase the concentration of antigen, the activity bound will be reducing, because increasing the fraction of stable inactive antigen will decrease the fraction of labeled antigen. And this is now calibration graph. So for example, you have an unknown sample, you find out the fraction of labeled antigen, and then you find out what is the concentration from this calibration graph. So it is a sub-stoichiometric antibody is in a very small concentration with respect to antigen, and then the decrease in the concentration of the antigen, labeled antigen, tells you what is the concentration of antigen in the unknown sample. So antigen labeled with radio tracer 125 iodine you can use, and then you can find out concentration of different hormones in the thyroid. The applications of radioimmunoassay are, like, for example, thyroid-related hormones and hormones of reproductive system, protein molecules, steroids, differential diagnosis of hyperthyroidism, neonatal hypothyroidism. But you can screen the newborns for the TCT. Very quickly you can do experiments. And there are tumor markers such as thyroglobulin, prostate-specific antigen, alpha fetoprotein, and carcinoembryonic antigen for diagnosis of cancer and screening of patients. In fact, nowadays, radioimmunoassay actually has taken a backseat, because there are now chemiluminescence, fluorescence-based techniques which can also reach the same sensitivity as RIA. The RIA can tell you the concentrations in nanograms, nanomoles. And so now the techniques are advancing, other techniques, and they are competing vigorously with the radioactive based techniques. So you will find that these techniques are also slowly being phased out, because if you can do the same experiment with a non-radioactive technique with the same sensitivity, then, and same cost of course, then there is no need for such techniques. But still many laboratories follow this technique. And lastly, I want to tell you the applications of radioactive tracers using in dating. Dating means finding out the age of an object. One of the objects, like for example, the rocks, geochronology. So you want to find out when that particular rock was formed. And this is based on the natural radioactivity series, 238 uranium decaying by alpha and beta to 206 lead. So you want to know, so you find out the uranium content and the lead content in the rock. So initially, let us assume that there was only, or even if there was some lead, then you will know, because all isotopes are not found by uranium decay. So you can find out what was the initial lead present in the rock. So the uranium present in today can be given in terms of initial concentration of uranium, exponential decay, e raised to minus lambda t. This is the time which we want to find out. Lead present today is uranium initial present minus uranium present today. So this is initial uranium minus present uranium is the lead present today. You can find out lead by mass spectrometry, and by solving these two equations you can find the time when this rock was formed using this expression. So if you measure the ratio of 238 uranium to 206 lead, you can find out the age of the when that particular geological sample was formed. And lastly, the carbon dating. Carbon 14 has half-life of 5,730 years, and it is being formed in the atmosphere by cosmic ray neutron bombarding nitrogen 14, and this carbon is reacting with oxygen to form carbon dioxide. By photosynthesis, green plants assimilate this carbon 14, and so much so that all living organisms in our body contain a specific activity of 15.3 ppm per gram. Disintegration per minute. 1 gram of any living organism will give you this much specific activity. But once an organism dies, then this activity is no more being accumulated, and so there will be a decay. And from that decay, you can find out what is the time. So if suppose the activity is A today, and initially till it was live was 15.3, by the same similar equation you can find out what was the time that this particular organic and the living organism died. So this is being used for carbon dating of fossils, wood samples, leaves, leather, charred bones, clothes, paper, so on. And since the half-life of carbon 14 is 5,700 years, about 4 half-lives of carbon 14, 20,000 years, and about half a half-life of carbon 14, about 2,000 years. This is the time zone which you can scan using carbon dating. If you want to go more than 20,000, there are other techniques. Similarly, tritium half-life is 12 years. So tritium dating can be used for water bodies, whether they are in contact with the rainwater or not. They are isolated water bodies will have less concentration of tritium. So these three isotopes are used for dating of different applications. So this was just a glimpse of applications of different radioanalytical techniques. I'll stop here, take up the next lecture next time. Thank you.